It's not easy that you can do it like that.
Right.
She has to put it very carefully. Ready?
Now, what's the blue tape for?
Okay, underneath here, there's little slots,
Okay.
and in order to get the ring back out, you stick a screwdriver in there, get behind the mold, and you wedge it out.
Gotcha.
A little bit here, a little bit there, a little bit
Otherwise,
here, a
the
little bit
building
there.
from the company was rectangular. That was for HMA mixed bounded HMA.
Gotcha.
But we are doing unbounded. We have to create our own ring, and that involved a lot of things to do this thing. Right? Hardest?
Yeah.
Yeah. I like.
The other thing is not only do we try to get the flat side down, we want three-dimensional so that the epoxy can grab onto the rock. Otherwise, if it's too flat, it's good, except for the epoxy can't grab on.
Gotcha.
So that's why you want three-dimensional. Now, if you have a rock like this and you lay it down, the epoxy is going to grab on, and when you go to, it's going to dry like that,
Gotcha.
which is going to leave a divot. So you would take that rock and you would put it that way.
Gotcha.
That way, when it dries, it kind of pulls it up together. And
Yep.
so now you have a flat side. It's not very big, but it is a flat side.
Gotcha.
So there's ways of putting them in there that have to be kind of careful. This is a good one. Well, not really, because again, it'll dry like that. And I just try to keep putting them in as close together, and so that there's a flat side down and three-dimensional as I possibly can. It takes sometimes about 3 to 4 hours to put one of these rings together. And yes, it is very tedious.
Focus on that.
This is good.
Okay.
This is not so good.
Gotcha.
So you have to think upside down,
Gotcha.
because you're not looking at this side, you're actually looking at the, this ends up being like this.
Good comparison.
And then when you take the ring out of it and you flip it upside down, then it becomes like this.
Perfect.
So you're thinking, when you're putting them down, what does it look like upside down? We'd end up with the ring with the rocks in it.
Right.
Then we end up putting glass beads on top so that the glass beads go in between the crevices of the rock.
Lock them in place.
Well, no, actually what you're trying to do is, and they'd be filled about halfway up the rock. Because when you put your epoxy mix in, you don't want it to run to the other side.
Gotcha.
So when you do the polishing, you're polishing rock and not epoxy.
Gotcha.
So I have a weight, a recipe, and I use tooling, resin. I use wolastanite, and that depends on the shrinkage, determines shrinkage. So I had to increase the amount of wolastanite so that the mold would go, instead of drying and becoming on level, it would shrink and actually lay flat.
Gotcha.
And then there's the silica, which takes up space, and there's a peroxide, which is a hardener. So we worked with different combinations until we got the right kind, so that the molds would lay flat, because what they do is they tend to shrink to the middle and then they get lopsided. Now if you put too much in, then it won't shrink around the individual rocks, and then you have pop-outs,
Gotcha.
which end up in mixture on that. But you end up mixing it in a bowl and literally pouring it onto your sample. And then once that's done, we take a weight and we lay it on here and we press down as hard as we can. And the excess epoxy mix oozes out, and that's good. So when you have this stuff,
Right.
and that just, when it gets hard after, you know, the next day, we leave it in overnight, then that just chips off, and it's easy to go to the next step. And then this just pops out. We take our screwdriver,
Right.
and we go in between the little crevices.
Yep.
We get behind and we kind of pry it out. We just keep going around and around and around until it comes out without cracking the mold.
Gotcha.
And the glass beads fall away. We don't test them. They're done. They did their purpose, and we go on to the next step.
Fantastic.
What he's doing now is wedging it in so that when this thing goes on, it won't
Rotate.
rotate. It's in there tight. So any kind of measuring or anything, the sample is going to be solid.
Gotcha. Excellent. So that's your circular track meter. Gotcha.
Now that never touches.
Right.
Yeah, just a, you know, laser depicted pictures, and to know how the aggregate is, macro texture is.
Gotcha. And it rotates around.
Yes.
Yes.
Okay.
I'm gonna place it.
This one, luckily, that doesn't have it. So you have the, you see how he does? You know, you marked it, right? Somewhere that you got keep it right there. You see that? See that?
I'm trying to center it
Center it as much as you can. Yeah.
right on top. This is the signal cable.
Power cable.
This is the power cable.
12-volt power supply.
Yes.
Yeah, the power supply we use battery.
Yep.
Power battery. Okay. The first reading was 1.4. The second is 1.41, which is a good indication that they are consistent, very close to each other. This is actually just a sketch of the profile of the sample.
Okay.
So it divides into 8 sections, as you can see on top of the circular meter. It sections the circle in 8 quadrants, like, so there is A, B, C, D, E, F, G, H.
Okay.
And this is the profile. You know, when it hits the top surface of the aggregates and comes back. So this is just showing us. We can actually,
That's okay. Go ahead with your reading. That's
you know,
just
I'm just enlarging them. So this is just the texture of the aggregate.
gotcha.
And when it calculates the average, the mean profile depth in millimeter is here, these numbers: 1.4 millimeter, 1.41 millimeter, 1.41 millimeter. The fourth one was 1.38.
These are the different sections that it takes a reading on,
Gotcha.
and then the
Yep.
sections show
And they
up
correlate to the spreadsheet.
Yeah, for example, this highlighted area is for section A.
Gotcha.
This one, section B, section, and it goes like that for the 8 sections. And at the end, so this area is the average. So from the 5 reading we have of the 8 sections, our average mean profile depth was 1.4.
Gotcha.
Okay.
But we borrowed it and we are going to send it once we get our new machine in.
Okay.
Mhm.
Give me a second. There we go. Okay, we're good.
Okay, this is a dynamic friction tester. We can use the sliders here for up to 12 times. I have already used this for 10 times, so I'm gonna change them with new.
Excellent. Yeah,
Rubber
I read the
sliders.
spec saying they recommended 12 times.
Yeah, 1911 says
Right.
that, yeah.
That, and we never take one set of sliders from quarry to the next quarry. We start with a new set of sliders,
Always.
always.
Always do
Yeah.
them on quarry so that we don't want to use some of the used one.
Because if we took a reading from one quarry, it may
It's
tear
gonna
up.
make different grooves.
Exactly, and then you take it to the next quarry, then the reading might be
Right. Off a little bit.
off a little.
Do you ever do, in asphalt testing, we call it a butter batch. We make a batch and then we throw it out and then we make our real batch. Do you ever make a trial run first just to groove the pads before doing the official runs?
We take 5 readings,
Uh-huh,
we throw out the first reading, and
gotcha,
we average the other 4.
gotcha.
Where is the panel? You're taking panel reading or tile reading?
Panel readings, that's where the verification panel
Yeah.
readings.
Mhm.
We take one test a month.
Okay.
Yeah,
We can do it later after
yeah, we
do
can,
this.
let's run the test and then.
With some water. During the test, it's supposed to have 1 millimeter of water film on top of the sample. I have some marks here, so I'm aligning them with the DFT so that it can be centered right on top of the sample.
That machine is about 49 pounds,
Okay. 49 pounds,
so
water flowing.
I'm gonna hook up this water pipe. I'm just trying to get rid of any trapped air bubbles.
Gotcha.
Alright. Okay, we have a set of cables here. One of them is a signal cable. The signal cable will take the data from the DFT to the controller, which will record the data. And the other cable is a power cable that brings the power all through from the source through the controller towards the DFT. My first choice is measurement mode. I'll give the file name, which is test sample 11. Okay. So everything is hooked up. Once I depress this handle, it's gonna rotate the plate underneath, which is very similar to this plate. The plate is gonna start rotating. It will accelerate up to 80 kilometers per hour.
80 kilometers per hour. Okay.
Once it reaches 80 kilometers per hour, the motor will stop, and the plate will drop on top of the sample. When it's rotating, it's not touching the sample. When it's accelerating to up to 80 kilometers per hour, it's not touching the samples.
Right.
Once it reaches 80 kilometers per hour, the motor stops, the plate will drop on top of the sample, and it will start taking measurements on top of the sample. Now it will slow down, and while it's slowing down, it will give us coefficient of friction at 60 kilometers per hour, at 40 kilometers per hour, at 20 kilometers per hour, and those results will be displayed on our controller.
Excellent.
So now I'll start the test. This will be one of the 5 tests that we are going to take on this sample.
Now, how many readings did it take?
This is where it has measurement, and it's also going to show a graph
Okay.
of the actual readings once it's done. Now, if you were to take these readings off of here and put them on the computer, you would just see thousands of numbers.
Right.
Because that's how many readings. It just takes thousands and thousands and thousands of numbers. And then, but in just a short time, it'll actually show you the average and it'll graph it.
Yeah, same deal. This is our set. Test data. We have three numbers, 20 kilometers per hour, 40 kilometers per hour, 60 kilometers per hour. We have three coefficient of friction of the sample. A lot of times the first readings tends to be an outlier.
Right?
So we don't consider that in our calculations. We will just take the average of the last four.
Okay, so you're gonna run some more tests?
Yeah.
All right, we're speeding up. You can hear it winding. We're at 30, 40, 50, 60, 70, and at 80, the brakes are going to go on. We're done.
That was a.
This is the state highways machine, right?
Yeah, this is.
We change at the beginning of the beginning reading and after the final reading.
I'm gonna take off the state DFT. So we have another DFT from Federal Highway just to check the repeatability and reproducibility of the test data. So I'll put it on the same spot that the state DFT was. Each DFT has its separate controller, so we're gonna start and do the same thing that we did with our DFT. Okay, the first test data was taken by Maryland State Highway DFT, and the second test data was taken by the Federal DFT. Now, if we see to the two sets of data, they are very close to each other. The average of the 20 km per hour coefficient of friction is probably 47, 48 here on the federal one. On the 40 km per hour, this is probably 44, the average, and on the federal it's 45, 41 or 42 on state DFT, and on the federal it's 44. So this is within our tolerance level. Our tolerance is 0.03. So we have a confidence of our data that both calibrated DFTs are reading the same numbers or within the tolerance range. The tires of the aggregate pollution equipment are right on top of the sample. I'm going to lower the guard. Okay, there is a safety pin here in case anything.
Now, what's holding the main sample in place?
The main sample is just sitting. Raise these legs that are supporting the aggregate pollution equipment so that the equipment will rest on top of the sample.
Gotcha.
I have an actuator here. I'll just lower it. Okay.
Gotcha.
Now, if you see at the legs, they are being raised, just like this
Gotcha.
is. All right.
I don't want to say we have to have it by end of the year.
I have
but,
another leg on.
I think some ideal. I don't
On
know
the
where
back.
we go. Maybe a second together.
So each sample is polished for 100,000 revolutions, okay, 100,000 turns of the three wheels. So I'm gonna set it or reset it actually. So we are starting at 0 and it's gonna stop. The ape is gonna stop at 100,000 revolutions. So we leave it overnight. It will run overnight, and it usually takes it about 36 to 37 hours to finish 100,000 revolutions. So when it stops, we are going to take our final reading after polishing. So I'm ready to start the polishing process. I'm gonna just start or turn on the motor. I'll check whether it's running on top of the sample, whether it's center